In this video, I'm going to go over this concept of linear quadratic regulator LQR controllers and specifically infinite horizon variation of it. So LQR is a form of a regulator problem. If you recall, we defined the regulation problem as driving the state of the system to zero as time goes to infinity using control. And we were specifically focused on linear systems of this form. And so far we saw and we particularly studied the linear feedback control minus kx. And we saw that if we substitute this full state feedback control into the system dynamics, we arrived at the system representation, and we saw that from internal stability concepts that we learned, we can drive the state of the system. We can make x go to zero as t goes to infinity if we design k such that a minus bk is Horvitz. And if you want to look at the block diagonal form, this controller acts like this and going to the system as control. And what we can do, and you have seen through extended control problems that we later looked at after designing this state feedback, this could also serve as an internal controller for other objectives as well. But for now, let's just focus on the regulation problem. So far, this was the controller that we designed. And usually we placed our design objectives or guided our design objective by pole placement. So we place the poles, for example, if you put them on the left-hand side away from the imaginary axis and have poles that their real part is very negative, you will have a fast response and you would converge to zero very fast. So the focus was mostly on the response of the system and the transient response and how fast or how slow the system is converging to zero. Now we want to look at this regulation problem from a different perspective, and that perspective is going to be that in the design that just focused on our transient response, we are not that much aware of the size of this control input that we are putting into the system. So in this alternative design, linear quadratic regulator, now our objective is going to be balancing how fast we want to converge to zero or how small we want to keep the state of the system versus how much energy or how much control we want to expend. So to create this balance between the state response and the amount of energy or amount of control that we are putting into the system, we have formulated this LQR controller, which looks at the problem in a different way. So the idea now becomes minimize subject to so now we are using to guide the design of our controller is this objective function, in which Q is a positive semi-definite matrix and R is a positive definite matrix. Overall, this is a positive term. And you can think of integral as adding up these terms at different times along the history of the system. And through this, what we are accomplishing is basically penalizing deviations of the state from zero. So the larger the states are, they are away from the zero. This first term is going to be positive, more positive. So your objective is to minimize this. So the objective of regulation is now to use a controller that keeps this amount small so the objective becomes small. But at the same time, we are not just focused on the states, we are looking at how much energy or how much control we are using, which is penalized by this second term, which shows the more the higher value compared to zero you are using, this term is larger. So now you are looking into finding a controller input which will keep the state small, but at the same time be aware of the size of the control inputs that go into the system. So just before going into derivation of this controller and what would be the solution of this linear quadratic regulator problem, I wanted just to a little bit open up this objective X transpose QX and U transpose RU and discuss the role of the Q and R weighting matrices in creating the balance that we are talking about, that how much weight you want to put on states and how much weight you want to put on the control expenditure. So to see this, let's just pick a simple case that we have two states. So technically this X transpose QX and U transpose RU, for each one, let's assume we have two states and two controls, just so we could see the dynamics of it. The Q is a matrix, and often we use a diagonal matrix. So I'm going to write this as Q11, 0, 0, Q22 times X1, X2. And so this is Q11, X1 square plus Q22, X2 square. And this one, if I assume two inputs, and as I said, we often use diagonal matrix for these R and Q. We end up with the terms like this. So the cost, the objective function, consists of these four terms. Now we can just look at one by one the role that these terms are playing. So Q1 and Q2, you can think about the weight that we place on the importance of the states. So for example, if we have a state that is more important to us than the other, what we could do is that we can put a higher weight Q11, for example. Let's say X1 is the state that is very important for us and we want to keep it as small as possible. So we would penalize deviation of X1 from 0 by choosing large Q1 values compared to Q22. And that's going to be how we regulate one state against the other. The same way, you can weight the importance on the input channels. So for example, if control channel 2 is more expensive, I'm going to penalize it more. So a small amount of U2, it's going to be having a large value because of the large R22 that I am going to use. And as a result, I am going to put more weight on making sure that the second channel, for example, is smaller as much as possible. And if I have to give up some of this deviation from 0, then it would come from, for example, channel 1. So this is just how Q1, Q22, and R11 and R22 play against each other. On the other hand, you can also compare Q11, Q22's relative size to R11, R22's size. So basically, we are comparing matrix Q and R. So the larger the Q is, it means that the states are more important for us. So we are putting more penalty on states, and we want them to keep them smaller. And similarly, if we choose a value that is large R compared to Q, it means that the control expenditure is important for us. So we are penalizing the use of the controller, and that's how we create this balance. And these Q and R are design parameters that we as engineers and designers will design for our system. And often it will take some try and errors, are looking at the response of the system, and some tuning that usually goes into picking the appropriate Q and R matrices for our problem. So now with this setting, what we are going to do is now look for what is the solution of this optimization problem. So this optimization problem, at first hand, if you look at it, it doesn't look straightforward. You have an integral over 0 to infinity. You are looking at the entire horizon of the system moving, and this is minimized subject to the state equation that we have. So technically it's challenging, but interestingly, because this is a linear system, there is some structural properties that linear algebra and matrix algebra enables us. And using those, I'm going to skip the derivations. The derivations are just a simple two-page walking through some matrix algebraic equations and are included in my complementary lecture notes. Here, I'm going to just give you the final solution. So if you walk through that optimization process, as we are going to see, this optimal control ends up, interestingly, being in a state feedback form, just like the state feedback regulator that we designed used pole placement to find the gains. But here, the optimal gains that minimizes our cost, they're going to come from a particular equation. It's not going to be up to us to decide it because this is an optimal control. The solution comes from the optimization procedure, and it would look like this. So the K matrix is going to have this value, where R is the R matrix that we have in our cost, P is the control matrix, and P is a matrix that comes from solving this algebraic Riccati equation. And so this is the algebraic matrix equations. And in the literature, we have some methods to solve for this matrix P. However, in this class, you're welcome to use MATLAB. And I'm going to give you the MATLAB codes. But before giving the MATLAB codes, I wanted just to give you an extended version of this objective function that is consistent with the notation that MATLAB is using. So a more general form of our objective function is this form that you see. Subject to x dot equal to ax plus bu. So this n matrix in many scenarios is equal to 0, but there could be problems that we want to penalize the cross-correlation, cross-relation between the states and the controllers. And for that, we can use this n matrix. So if you end up using this more general case, which is sometimes not actually that common, the equations change slightly. The optimal control in this case, it's just going to be very similar to what we had. It's still a state feedback. The gain K, it's going to include a term N, and the algebraic Riccati equation also that gives us the P matrix equal to 0. So if we consider this matrix structure, MATLAB has a simple command, which is the LQR command. You can use it in a format like this. This is LQR. You provide the A, B, Q, R, and N, and many times you can put N equal to 0 or empty. And what it would give you is going to give you the gain. It would also give you P, unique positive definite solution of Riccati, algebraic Riccati equation, and E is the closed loop eigen values of A minus BK. So this is going to be how we use the LQR control and what's the story behind it.